Let's start with a question. If you're driving a car and you want to turn left, what do? You turn the steering wheel. Groundbreaking stuff, I know, but have you ever looked into a train's cockpit? No steering wheel, just levers, screens, and a lot of coffee. So, how does a 500-ton behemoth negotiate a curve at 200 kilometers per hour without just choosing to go straight into a field? You might say, well, obviously, it has a differential like my car. To which I would say, nice try, but no. A car's differential allows the outside wheel to spin faster than the inside wheel because it has more ground to cover. But a train's axle is a solid piece of steel. Both wheels are locked together. They must spin at the exact same speed. If they were simple cylinders, the train would literally grind itself off the tracks or screech until the metal melted. This is where the first bit of engineering wizardry comes in, the cone effect. If you look closely, and I mean really close, maybe don't put your head that near a moving train you'll notice that train wheels aren't flat cylinders. They are cones. They have a subtle slope, usually around 120. When the track curves to the left, centrifugal force nudges the train to the right. This pushes the right wheel on to its thicker part of the cone, and the left wheel on to its thinner part. If the right wheel is now effectively larger in diameter than the left wheel, but they are spinning at the same RPM, what happens? Exactly. The right wheel covers more distance per rotation. The train steers itself. It is a purely mechanical, automatic, and frankly, genius solution that requires zero computers. Take that, Silicon Valley. We've been using self-driving tech since the 1800s. We just called it geometry. But this low friction life comes with a price. Steel on steel is incredibly efficient rolling. Resistance is up to 5 times lower than a rubber tire on asphalt. But low friction is a nightmare when you need to stop or climb a hill in the rain. To solve this, engineers turn to the beach. Meet the sanding for life system. When the locomotive's brain detects the wheels are slipping on wet or icy rails, it just hope for the best. It uses compressed air to blast special silica, sand directly under the wheels. It's basically like creating a temporary sandpaper road in front of the train to instantly boost friction. If you've ever wondered why there's random sand on a bridge in the middle of nowhere, now you know. You're welcome. Now, once we've got all that mass moving and we eventually want to stop, we don't just throw away that energy. Modern trains are essentially giant mobile power plants. Through a process called regenerative braking, the traction motors reverse their roles. Instead of consuming electricity to turn the wheels, the spinning wheels turn the motors, generating electricity. This power is then pumped back into the catenary wires, or the third rail for other trains nearby to use. We are literally stealing the momentum of a stopping train to help the guy behind him get up a hill. It's the ultimate pay it forward, but with high voltage dig. So, we have cones for steering, sand for gripping, and we're recycling energy like a green tech startup. But all this weight and efficiency put an unimaginable strain on the ground itself. You can't just lay steel on dirt. You need a permanent way, and that, my curious friends, requires us to talk about why engineers are so obsessed with very specific types of rocks. In the previous section, we talked about how trains move and steer, But what exactly are they moving on? You might say tracks, and I'd say congratulations, you have eyes. But to an engineer, this is just a pair of steel bars. It's the permanent way, and if you think laying track is just a matter of tossing steel on to some dirt, you're about to have a very bad, very expensive afternoon. If you put 500 tons of moving steel on top of soft, wet soil, what happens? Exactly. Your multi-million-dollar locomotive becomes a very shiny, very permanent lawn ornament. To prevent the sinking locomotive scenario, we need a track foundation that distributes weight. This brings us to my favorite part of railway engineering, specific rocks. Look at the stones under a track that's ballast, and no, you can't just go to the beach and grab some pretty, smooth pebbles. Why? Because smooth things slide. If the ballast slides, the track moves. If the track moves, well, refer back to the lawn ornament scenario. Engineers are obsessed with angular, sharp, edged granite or basalt. These rocks aren't just sitting there, they are interlocked like a 3D jigsaw puzzle. When a train passes, they jam together, providing stability, damping vibrations, and crucial, draining water so the whole thing does turn into a swamp. Plus, they're so hostile that plants can't grow there. It's the only place on Earth where being edgy is a functional requirement. Now, let's talk about the infinite rails. Back in the day, you knew you were on a train because of that rhythmic clack, 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 clack sound. That was the sound of wheels hitting the gaps between rail sections. Those gaps were there to allow the steel to expand in the summer. But the clack, clack is dying. Modern engineers use thermite welding to fuse rails into miles-long, continuous strips. This is great for a smooth ride, but it creates a terrifying physics problem. If a 3-mile-long piece of steel gets hot in the sun, and it has no gaps to expand into, where does that energy go? Normally, the rail would buckle like a cooked noodle. To counter this, we have to use brute force. We pin the rails down with massive concrete sleepers and bury them in that jigsaw puzzle ballast. The track is literally held in a state of internal war, wanting to expand but being physically bullied into staying straight by thousands of tons of rock and concrete. Speaking of concrete sleepers, fun fact, the official engineering requirements for a good sleeper in some regions include that it shouldn't be easily damaged by anti-nationals. I'm not making that up. It's in the manual. So, if you're planning a revolution, maybe don't start with the sleepers. They're tougher than your ideology. But even these indestructible steel and stone systems have a weakness you can't see with the naked eye. Corrugation, or as I like to call it, the invisible waves. As wheels roll, they create microscopic vibrations that eventually knead the surface of the steel into tiny, invisible waves. This corrugation makes the train louder, and eventually vibrates the entire track to pieces. To fix it, we use rail grinding transient fire, spitting machines that move at a snail's pace, grinding the steel back to a perfect profile. So, we have a system that fights thermal expansion with brute force, uses puzzles made of granite to stay dry, and requires regular exfoliation from fire, trains to stay smooth. It is a masterpiece of static tension, but all of this infrastructure has one job: to support the permanent way through the most difficult terrain on Earth. And sometimes the terrain is so difficult that laying tracks isn't enough. Sometimes you have to go through the mountain or over the valley, which means it's time to talk about the things that keep civil engineers awake at night: bridges and tunnels. Welcome to the part of the video where we stop talking about how it should work and start talking about how humans actually made it work. Because, let's be honest, engineering is often just the art of managing someone else's crazy idea. If you are an architect in Chongqing, China, and a high-speed monorail line is planned exactly where your new 19th-story apartment building is supposed to go, what do? You don't move the building, you don't move the train, you simply build the station inside the 19th floor. This is the world of railway oddities, where the laws of physics meet the stubbornness of mankind. Let's talk about paranoia. Everyone loves a good secret, but Joseph Stalin took it to a civil engineering level. Beneath the already deep Moscow metro, which was designed to double as a nuclear bunker with massive hermetic pressure doors, there is a legendary parallel system known as Metro 2. Why build a secret train if you might need to leave in a hurry using a car? Stalin's answer was simple: embed the rails in concrete. This allowed the tracks to be used by both specialized trains and standard automobiles. It is the world's most expensive driveway, hidden 100 meters underground, connecting the Kremlin to the headquarters and a secret airport. It's a perfect example of how the permanent way can be modified for rubber tires when the leader is sufficiently nervous. Now from the depths of Moscow to the roof of the world. In Peru, the Ferrocarril Central Andino has to climb from sea level to an oxygen, starved for 782 meters. As we learned in the previous part of the video, trains hate steep grades. Anything over 4 is basically a wall for a 500-ton machine. So how do you climb the ends? You don't use a spiral. You use switchbacks. The train pulls into a dead end, a worker flips a switch, and the train continues up the next zig of the mountain backwards. It's so high that they have doctors on board with oxygen tanks for passengers suffering from altitude sickness. It is engineering by way of a 3-point turn on a continental scale. But what if the challenge isn't a mountain, but pure, unadulterated mass? Let's talk about NASA. When they need to move the rocket boosters for the Artemis mission, they don't call a trucking company. Why? Because a single booster segment weighs 180 tons. If you put 180 tons on a standard rubber tire, what happens? You don't have a road anymore, you have a trench. But thanks to that 5 times lower rolling resistance of steel, steel we discussed, NASA uses special reinforced railway cars. These are the weightlifting champions of the rail world. If you think your commute is heavy, just remember there's a train out there carrying enough explosive power to leave the planet, resting on a standard 1,430 5mm gauge track. Speaking of sharing space, let's visit Thailand for the most stressful grocery shopping experience on Earth. The Meklong Railway Market. Here, vendors sell fish and vegetables literally on the tracks. Socratic logic: if a train is coming 8 times a day, wouldn't you move the market? Nope, you just build the stalls to be retractable. When the siren blares, the awnings pull back, the baskets of goods are nudged just centimeters from the rails, and the train passes directly over the bananas. Within 10 seconds of the caboose passing, the market is back to normal, as if the 50-ton locomotive was just a minor breeze. It is a masterpiece of cultural adaptation and very, very precise measurements. Finally, let's look at the ghost trains of Britain. These aren't haunted there, a legal loophole. Because officially closing a rail line in the UK is a bureaucratic nightmare involving years of public hearings and millions in costs, companies sometimes find it cheaper to just keep running the train. They are called parliamentary trains, and they might run once a week at 4 a.m. with 0 passengers, just to keep the line open. It is a ghost-like ritual of steel and law, where a 100-ton machine moves through the dark purely to satisfy a piece of paper. It reminds us that sometimes the most rigid part of railway engineering is the steel, it's the rule. Now, let's see where those rules are taking us in the future. So far, we've looked at the permanent way as a gritty, heavy world of sharp rocks and brute force. But we are currently entering an era where the steel part of the railway is becoming optional, and the driver part is becoming a relic of the past. What is the single biggest enemy of a train trying to reach the speed of a jet plane? You might say gravity, but magnetism has that covered. The real answer is friction. Even with our 5 times lower rolling resistance of steel on steel at 600 kilometers per hour, the mechanical parts simply can't handle the heat and vibration. Because of this, engineers decided to stop rolling and start flying. This is Maglev, Flight Without Wings. It is arguably the first fundamental innovation in railway travel since George Stephenson's rocket took its first puff of steam. Maglev uses powerful electromagnetic systems to uplift the train, guide it laterally, and propel it forward. Because there is zero mechanical friction between the train and the guideway, the only thing slowing you down is air resistance. If there is no contact, there is no wear and tear on the tracks. Right. Exactly. Maintenance costs for the guideway drop significantly because you aren't grinding steel into dust every time a train passes. The Japanese Zero Series Maglev recently proved this by hitting a mine, melting 0 Kelvin. At that speed, you aren't just taking a train, you are riding a terrestrial missile that happens to have a snack bomb. But what is the point of a train that moves at 600 km if it's still controlled by a human with the reaction time of, well, a human? This brings us to the next paradigm shift, the driverless view. Modern metro systems are increasingly moving to go, afar communications-based train control, grade of automation 4. What does grade 4 actually mean? It means the train is 100 autonomous. There is no driver, no cabin, and no one to judge you for eating a messy kebab at 8 a.m. Because the system uses high-speed day to transmission to coordinate train positions in real time, it can reduce the headway gap between train stow as little as 90 seconds. For you, the passenger, this means a unique experience. You can sit at the very front of the train and look through a massive window directly into the tunnel. It's like being in a sci-fi movie, watching the illuminated concrete hoops fly past as the computer handles the rocket science of not hitting the guy in front of you. Now, if we are going to have autonomous missiles flying through tunnels, we need to be absolutely certain those tunnels aren't going to collapse. How do you check for structural failure in a concrete wall that is buried 50 meters underground? Traditionally, you send a tired engineer with a flashlight and a clipboard. But the future is much weirder. EOT in the concrete. In massive projects like the Grand Paris Express, engineers are now embedding vibrating wire day, the loggers directly into the precast concrete segments before they even leave the factory. These sensors are encased in rugged polymer and resin, effectively making them part of the bone of the tunnel. They are powered by internal batteries that can last up to a decade without anyone ever touching them. From the very moment the tunnel boring machine BEM clicks a segment into place, the segment starts talking to a gateway. It reports its own internal stress, strain, and temperature. We are literally building tunnels that can feel pain and tell us about it before they even think about breaking. Let's look at the causal chain of this tech. Since the concrete can monitor itself, we don't have to stop the tunnel boring machine for hours to manually install sensors. And if we don't have to stop, the construction becomes 25 faster. Consequently, we can build deeper, safer, and more complex networks than Stalin ever dreamed of for Metro 2. This synergy between Maglev speed, Goa fire autonomy, and EOT structural intelligence is transforming the railway from a 19th century mechanical beast into a 21st century biological organism. It is a system that knows where it is, feels its own structural health, and flies without ever touching the ground. We are moving toward a world of space-time convergence where the distance between cities is measured not in kilometers, but in the few minutes it takes for a magnetic pulse to hurl you across a province. But before you get too excited about your 600 commute, remember that even the smartest computer still has to deal with the most unpredictable element of all, us. The history of railways is just a story of magnets and sensors. It's a story of how we changed the world to fit the tracks, and how the tracks, in turn, shrunk our world. As we wrap up this journey, we have one final question to answer. Is the railway just a way to get from point A to point? Or is it the very thing that makes point A and point worth visiting in the first place? It's time for the philosophical payoff. We've spent the last 15 minutes talking about conical wheels, specific types of granite, and EOT sensors embedded in concrete. Is a railway actually a thing? Is it just a collection of steel bars and heavy engines? If you look at it through the lens of a historian, the answer is no. A railway is a time machine. It is the most powerful tool for space-time convergence that our species has ever devised. Before the train, the world was a collection of isolated islands of humanity. Travel was a gamble with death. But then came the steam engine. As a result, the very concept of being far away was murdered by a few pieces of smooth steel. Let's talk about the first detail that changed everything, the shrinking of the world. If you lived in New York in 1830 and wanted to go to San Francisco to, I don't know, look for gold or escape a bad ex, how long would it take? Half a year, 6 months of grueling wagon travel, disease, and crossing mountains. But in 1869, the transcontinental line was completed. How much did it shorten the trip to one single week? Imagine that. In the span of a few decades, we reduced the size of the continent by over 95. This suddenly unlocked a vast pool of resources and new agricultural regions. The train didn't just move people, it integrated the economic life of nations into a single beating heart. But the train didn't just conquer space, it had to conquer time itself. This is our second detail, standardization of time. Before 1855, every town had its own time based on when the sun was highest. If it was 12:0 in London, it was 12:05 in Bristol. For a traveler, this was just annoying. For a train dispatcher trying to prevent two 500-ton machines from meeting on a single track, it was a death sentence. To prevent this, the railway forced us to become obsessed with precision. In 1855, Great Britain introduced Greenwich Mean Time (GMT) as the global reference point for rail scheduling. We literally redefined the way the human race perceives the passage of the day, just so the trains could run on time. When you look at your watch or your phone today, you aren't looking at nature's time, you are looking at railway time. Which leads us to our final realization, the railway as an awakening. When you see a train today, whether it's a high-speed Shinkansen in Japan or a rusty freight train in the Midwest, don't just see a machine. What are you actually looking at? You are looking at the result of thousands of years of innovation in metallurgy, logistics, and physics. It is the artery of the national economy, a hero story of a technology that survived the rise and fall of empires. From the wheel gauge reduction we discussed in previous chapters to concrete sensors for the Internet of Things, every millimeter of the railroad track is a testament to human perseverance. We refuse to be limited by our legs. We refuse to be limited by the mountains. But we also learned that even the most advanced autonomous system still rests on sharp rocks and simple geometry. So the next time you sit in a station and feel that soft whoosh as a train glides in, take a second. Realize that you are part of a system that shrunk our world so we could share it. The history of the railway is the history of modern civilization. It is the backbone that holds us together, even when we're moving at 300 kilometers per hour. But enough of my late night philosophia, let's talk about you. Question for the comments. Did the fact that trains steer themselves with cones blow your mind as much as it did mine? Let me know, because honestly, I'm still not over it. If you're still here, you clearly have a passion for things that are heavy, fast, and engineered to perfection. If you want to dive deeper into the hidden infrastructure of our world, hit that subscribe button, and maybe, just maybe, next time you are at a crossing, give the train a little nod. It's been working hard for us for 200 years. Thanks for watching.